Welcome to this explainer. Today, we're skipping the textbook theory and stepping directly onto a virtual job site to tackle a very specific real-world scenario from the Canadian Electrical Code. It's one of those things that totally trips up seasoned professionals and apprentices alike. We're talking about the surprisingly strict rules surrounding transformer installations, where just a few missing millimeters can literally mean the difference between a high five from the inspector and a completely exhausting, costly rebuild. Okay, let's set this scene. Imagine you're on the job right now. You've been tasked with mounting a three-phase dry-core transformer directly to a concrete block wall. Now, this equipment is incredibly heavy, the schedule is tighter than ever, and you need to know exactly how much space is required directly behind it, right between the transformer enclosure and the block wall itself. And let's be real, just guessing is absolutely not an option when the inspector shows up with a tape measure. So you pause, consult your plans, and try to jog your memory. You've got 4 potential clearance options floating around in your head. Is it a tiny 6 millimeters? Is it 50 millimeters? What about 150? Or do you need a massive 300 millimeter gap? Well, before we just give you the answer and move on, we really need to understand the physics and the core safety rules that actually drive these specific numbers in the code handbook. First, let's anchor ourselves in reality here. If you look closely at a typical dry-type transformer, you'll immediately notice the distinct ventilation grills on the front and sides. Now, these aren't just cosmetic. They are absolutely crucial to the safe operation of the equipment. The whole enclosure is specifically designed to let free-flowing air move right through the chassis. Honestly, before you even try memorizing any code numbers, you've got to understand the physical reality of these devices. A fully loaded, dry-core, open-ventilated transformer generates a massive amount of heat. Since it doesn't have cooling oils or liquids, it relies 100% on ambient, free-moving air to keep itself from overheating. If that airflow gets restricted, the heat transferring to adjacent surfaces could easily spike those surface temperatures right up to their auto-ignition points. In plain English, it becomes a catastrophic fire hazard. Because of that intense heat, the code lays down some really strict baseline rules. The main takeaway here is that for general, floor, or adjacent surface clearances, a non-combustible surface needs a minimum of 150 millimeters of airspace. But if that adjacent surface is combustible, say a plywood wall, that required distance safely doubles to 300 millimeters. It's fascinating how the code actively adjusts the clearance requirements based entirely on how flammable the surrounding environment is. For instance, check out a standard floor-mounted installation. This is exactly where those general 150 millimeter and 300 millimeter separation rules perfectly apply. That invisible cushion of airspace all around the unit is what keeps the nearby walls and equipment safe from the intense radiant heat blasting out of that metal box when the system is running at full load. But here is where the plot thickens. Let's pivot back to our specific scenario and see how this all changes when the transformer is physically mounted directly onto the wall, rather than just sitting next to it on the floor. Rule 26-246 Subrule 3 introduces a whole new set of variables that actually completely override that general 150 millimeter rule we were just talking about. So to solve our job site mystery, and more importantly, to pass that inspection, we just need to run through a quick 3-step mental checklist dictated by the handbook. Step 1. What's the wall material? Is it combustible or non-combustible? Step 2. Based on that material, do we need any specific heat shielding? And finally, step 3, once we've nailed down those details, we can apply the exact clearance measurement from the code. Let's look at the combustible wall scenario first, just to see how strict things can actually get. If you are mounting this heavy transformer to a combustible wood wall, the code demands some serious protection. You essentially have 2 options. You can use a non-metallic, heat-insulating backer to protect the wood, leaving a 6 millimeter air gap in front of that backer. Or you can go with a grounded sheet metal shield. But if you choose the metal shield, you need a 50 millimeter air gap behind the metal, plus an additional 6 millimeter gap in front of it before the transformer enclosure even begins. It's a whole process. Thankfully, our specific scenario is a lot simpler, but it still heavily relies on knowing the exact wording of the code. Remember, we're mounting to a concrete block wall. Concrete is inherently non-combustible. And that leads us straight to the precise wording of Rule 26-246 Subrule 3 Item A. It clearly states that if the adjacent surface is the wall on which the transformer is mounted, and that wall is non-combustible, the minimum permissible separation changes entirely. All right, with the context of heat dispersion, that baseline 150 millimeter rule, and all those specific material combustibility exceptions fresh in our minds, let's jump back to our original question. You are holding that 3-phase transformer on the job site right up against that concrete block wall. how much space is required between the unit and the block wall. Do you have your guess locked in? The correct answer, pulled directly and exclusively from the Canadian Electrical Code Handbook for a non-combustible mounting surface, is exactly 6 millimeters. Not 150, not 50, but a remarkably small 6 millimeter gap. That's barely a quarter of an inch. Because the concrete acts as a non-combustible heat sink, that massive 150 millimeter requirement for floor-mounted adjacent surfaces gets safely reduced to almost nothing when you're wall mounting. So why does all this matter? Well, knowing that a wall-mounted non-combustible surface requires just a tiny 6 millimeter gap instead of the standard 150 millimeter general clearance definitely ensures your installations are perfectly compliant, but it also ensures they're structurally efficient. I mean, if you didn't know this exception, you might end up burning hours fabricating a huge custom bracket just to hold a massive transformer 150 millimeters off a solid concrete wall. You'd be wasting time, wasting money, and honestly, just making your life way harder than it needs to be. Precision and understanding the code makes you a better, faster, and much safer professional. Which leaves us with one final thought to chew on. If knowing how drastically a simple material change, like swapping wood for concrete, can alter the rules from 300 millimeters all the way down to just 6, are you fully prepared to spot the next critical exception in the codebook before it completely halts your project? The code isn't just some boring list of numbers. It's a living, dynamic system of physics and safety. Keep learning, keep questioning, and we'll see you in the next explainer.
For more sample question, follow us.